Hello everyone, welcome to MindMatrix. So in this lecture, we will be solving some questions from GATE DA sample paper. So before that, you can also visit our website. So this is mentioned here, www.mindmatrix.net.in. Yeah, so those who are new to our channel, so let me introduce myself. My name is Anshul Sharma. I'm upcoming software engineer at Juniper Networks. Currently, I'm pursuing MTech in computer science from IIT Kanpur. I have 2+ years of teaching experience and mentored more than 1,000 students as of now. I have the expertise in computer science and data science subjects. I have secured All India rank 294 in GATE Computer Science, cleared ISRO NEELIT exam, and also got selected as Administrative Officer at AIC. So these are our premium courses that have already been launched on our website. You can visit our website, and one course is for GATE CSE complete course for 2025 and 2026. For GATE DA also we have launched both for 2025 and 2026 complete placement preparation course, and as a combo we have also launched GATE CS and GATE DA complete course. This complete placement preparation course is already included in these packages, that is for CSE, DA, and in the combo. So you don't have to enroll in it separately. Fine. And classes has already started, so you can enroll and you can start your preparation for GATE Computer Science and GATE DA. And if you want to see the quality that we are providing in our premium courses, so what we have done is we are providing operating system for free. So you can enroll in this course. The link will be given in the description below in this video, and you can just visit it and you can enroll for free and start attending the lectures. We are providing the live classes for operating system. Okay, so you can see the quality and you can learn from our premium educators. Okay. You can also connect with us. So this is the QR code for our website, this is the QR code for our doubt discussion Telegram group, and this is the QR code for our WhatsApp channel. You can join all these and you can connect with us, okay, for your doubts and all the queries related to the courses and all. Fine. So let's start with the first question here, that is from DBMS. Let's read the question first. Consider two relations. One is R and this is having two attributes X and Y. Other one is your S having two attributes X and Z. Relation R has 100 records and relation S has 200 records. What will be the number of attributes and records of the following query? So this query is given to you and you have to find out the number of attributes and the records in the result. So query is select star, that means select everything from R, cross join S. So you are between these two relations, you are making a cross join. Okay, cross join means as you have this relation R, so these are two attributes X and Y, and here you have S, two attributes X and Z. So for every tuple, for every row of this R, you are going to form a row with a tuple in S. Basically, let me give you an example. Let's say it is A1 and here it is let's say B1 for example. Now if you just have, let's say you just have this data in the relations. So if you are going to perform cross join on R and S, so in the result you will be getting, let me denote it, R dot X. So here it is going to be R dot Y, S dot X, S dot Z. So for each tuple you are going to perform a cross product in the for with each tuple of S. So you will be getting A here, 1 here, B here, and 1 here. Suppose let's say you have A2 also. So here also you will be getting A here, 1 here, A and 2. So are you getting, for every row you are going to perform cross product with each row of S. Similarly, if you have more data here, again you are going to perform cross product. Okay, and if you see here you have a common attribute, but we are not performing natural join here, it is a cross join, so it will be considered as different attributes, one for R and one for S. So don't get confused in that. Okay, now so our relation R has your 100 records and relation S has 200 records. So we know after performing the cross product, the total number of records we are going to get will be 100 multiplied 200, and that is going to be what? 20,000 records. Correct? 20,000 records we will be getting in the final result. And what about the attributes? As I told you, you will be getting 4 attributes here. So if you see the options, option B is the correct answer here, 4 attributes and 20,000 records. I hope it is clear to all of you. Let's proceed to the next question. Here we have question number 2. Consider two relations R and S. R is having 2 attributes X and Y, and S is having only 1 attribute, that is Y, and perform the following operation. So this is the operation we are performing. So R divide S. So it is performing divide operation, division operation it is performing. If X is the relation returned by the above operation, that means the result final, which of the following options is or are always true? So in order to solve this question, we need to consider we need to take some examples. Okay. So let's say here, let's say this is my relation R, and here we have 2 attributes X and Y, and here as we have S, and it is having 1 attribute, that is Y. Okay. Let's say if I'm having the data like this, A1, A2, B1, B2, C1, C2. Okay. Let's say, let me add more data just for more clarity. Let's say we have A3 also, B3 also, C3 also. Fine. Now let's say in S, this Y, we have 1, 2 and 3. Now if I perform division operation, so what happens in division operation? For this, we have to consider like this. For 1, like we have 1, 2, 3. In this we have 1, 2, 3. So we have to select, basically in the final result we will be getting X attribute in the final result. So for 1, 2, 3, whatever we have in this, all the values, we have to check in this relation R whether we have any value of X for which all these 3 values exist. So if you see carefully, for A we have 1, yes, for A we have 2 as well, and for A we have 3 as well. That means in the final result A will be there for sure. Clear? What about this B? So for B, if you see carefully, you have 1, yes, you have 2 as well, and you have 3 as well. So you will be getting B as well. What about 3? Yes, C will be there, because for C you have 1, you have 2, you have 3, so C will also be there. This is one of the examples. So if you carefully see here, we can say from this that definitely X, the cardinality, basically this denotes the cardinality. That means the number of tuples we have. So the cardinality of X will always be less than equal to the cardinality of R. Yes or no? Because you cannot have more than that, we have seen here. Now let's consider one more example or 2 more examples. Let's say if I don't have this B3, if I don't have this B3 now, consider this. So in that case, what will be my result? I will be having 1, 2, 3 I have for A and for C, but not for B. For B we have 1, for B we have 2, but we don't have 3 for B. So in the result, I will be getting A and C only. So after taking these 2 examples, we can clearly say that yes, cardinality of X will always be less than equal to cardinality of R. But in the options, they are also talking about cardinality of S. So if you see this example, first example, you can see the cardinality of X is, equal to this, right? Equal to S, because here also you have 3 and here also you have 3. In this case, you can see it is 2 and it is 3. So can we say that always the cardinality of X is less than equal to cardinality of S? Before moving to that conclusion, let's take one more example here. Okay, just for more clarity. Let's say you have X here and Y here. That is your relation R. Fine. What you have here is 1A, 1B. Let's say you have 2A, 2B, and you have 3A, 3B. Fine. Now if you talk about this relation S, let's say you have in the Y attribute, you have what? A and B. Now if you perform division operation, what do you get in the result? What do you get in the result? So for AB, if you see this entirely AB is present for 1, yes, so that means 1 will be there in the result for sure, yes. AB is present in for 2 also, so 2 will be also be there. AB is present for 3 as well, so 3 will also be there in the result, yes or no? Now from this example, can we say that here in this case, cardinality of X is greater than cardinality of S, and it is talking about always true. So we can say this is not always true. As we have seen in this example, this is not always true. This is also this is also a possible case here. But we can say clearly that option A is correct, because always cardinality of X will be less than equal to cardinality of R. You can take any example you want, because we can also see it like this, that X into S, or the Cartesian product, will always be the subset of R. This is also true. Whenever you are performing division operation, this is also always going to be true. So here you can see, whether you perform the cross product, whatever you do between X and S, it will always be a subset of R. So definitely it is true that X is, cardinality of X is less than equal to cardinality of R. So this we have proved that this is not true in this case, and here also this is same as mentioned, so option C is also incorrect, and option D is always incorrect. So that is the answer. Option A is the correct answer for this question. Clear? Let's proceed to the next question. Question number 3. Which of the following statement is or are true? So this is MSQ question. This is also MSQ question. Option A is every relation in BCNF is also in 3NF. So this question is based on normalization. If you talk about BCNF, let's say we have this functional dependency X determines Y. So when can we say this is in BCNF? When X is your super key. If this is the condition, then your relation is always in BCNF. And to be in a BCNF, first it has to be in 3NF. That is also true, right? So can we say every relation in BCNF is also in 3NF? Yes, first it has to be 3NF. It has to be in 3NF, then only we can check for BCNF. Then we check for BCNF. So option A is true. It has to be in 3NF, then BCNF. And this is also true, because in 3NF, let's consider the same case. What is the condition? Transitive dependency should not be there. That means either X is going to be a super key or Y is your prime attribute. So there is a option here, prime attribute, or set of prime attributes basically. So you have the choice here, either this is true or this is true, then the relation is in 3NF. And in case of BCNF, this is mandatory, that X has to be a super key. Okay, so we can say that first a relation has to be in 3NF, then only we can talk about BCNF. Okay, so option A is correct. Every relation with 2 attribute is in BCNF. It is talking about the binary attributes. So as we have considered this case only, let's say we have a relation having A and B as the attributes, and if we have the functional dependency like this, A determines B only. So if I find the closure, I will be getting A and B as well. That means A is my super key, candidate key also, and super key also basically. So A is able to determine all the attributes present in the relation. So can we say this is in BCNF? So always remember this, as I have given the example also, that every relation with the 2 attribute is always in BCNF. This is true. B is also correct. Option C, no relation can be in both BCNF and 3NF. Yes, it can be. This relation is in 3NF and BCNF. So this is incorrect. Every relation in 3NF is also in BCNF. No, it is not true. This is true, but its vice versa is not true. We can have a relation which is in 3NF but not in BCNF. Okay, so this is also incorrect. Let's proceed to the next question. So here we have question number 4. Given the following relation instances, so we have 3 attributes X, Y, Z, and the tuples, the rows are given to us, the data is given to us for these 3 attributes. Now we have to find which of the following conditions is or are true. So here let's consider option by option. Option A is saying xy determines z. When I say xy determines z, that means the combination of xy will uniquely determine z. So let's check whether it is true or not. If you see here, 1 and 4 combination of xy, so 1 4 determining 2, fine. Now do you have 1 4 again? If you see, first check, 1 4 is determining 3. I told you that it has to be uniquely determined z. So 1 4 is determining 2, but here 1 4 is determining 3 as well. So that is not correct. So you can clearly eliminate this option. Option A is not correct, because and condition is there. If you have checked this one, so no need to check. If the first condition is false, no need to go for the second one, because the entire option is incorrect. But still, if you want to check, you can check. Z determines y. So 2 determines 2 determines 4, 3 determines 5, and 3 determines 4. That is also incorrect, right? Because Z has to uniquely determine y, and 3 is determining 5 as well, and 4 also. So that is also incorrect. What about option B? YZ determines x. YZ determines x. 4 2 determines 1 uniquely, fine. 5 3 1, 4 3 1, 5 2 1, 2 1 3. So that is correct. This one is correct. What about x determines y? 1 determines 4, but 1 also determining 5. So this is incorrect. 1 has to uniquely determine y for as per this condition. So this is also incorrect. What about option C? Y determines x. So if you see here, 4 determines 1, 4 determines 1, 5 determines 1, and 5 determines 1. That is correct up to this. 2 determines 3. That is also correct. What about x determines y? We have already checked for this. So this is also incorrect. Right. What about option D? Xz determines y. Xz determines y. 1 2 determines 4, 1 3 determines 5, and 1 3 determines 4 as well. So not possible, right? So this is also incorrect. So as per this question, they have given the question in the sample paper, but the option, none of the option is correct here. None of the option is true here. Okay. Sometimes it happens, but yes, it is just a sample paper. So maybe they haven't, give a thought, for verifying the answers also. So it's fine. Let's move on to the next question. Let's see here, question number 5. So this question is based on B plus tree. This question is based on B plus tree. Let's read the question here. A file with 1 lakh records is indexed with B plus tree. Okay. If the size of a memory block is 2k bytes, the size of a key is 4 bytes. The size of a pointer is 4 bytes. We have to find the minimum possible height of the B plus tree index. And height is always greater than or equal to 1, they have mentioned. They have also given you the hint that no records are stored in the nodes, only keys are stored. And that is also the property of B plus tree. You have the records at the leaf level only. Okay. Only keys and block pointers are there in the internal nodes. The sizes of the pointers are same, irrespective of whether they point to a node or a record. That means block pointer size or the key size is same. Okay, now let's see here. In case of B plus tree, we know this. Let's understand this. The structure of the node, that is important to understand this. So we have a block pointer here, which is going to point to the next node. Then we have key. Then we have block pointer again. Then we have key, and then we have block pointer again. It's like this. The structure is like this. That means we have 3 block pointers and we have 2 keys. Just for example, I'm taking, but this is the structure for B plus tree. You can have the point here is you can have n block pointers or n pointers, you can say, and n minus 1 keys will be there. N minus 1 keys will be there in B plus tree internal nodes. So we have to first find the order. What is the order of this? So order of B plus tree is going to be the number of pointers you have, in the node. So can we say we have n multiply the number of pointers, okay, or basically not the number of pointers, basically the size of the pointers. So can we say in order to find the size of this memory block, the size of the memory block is already given to us, that is 2k bytes. So can we say n into pointers, that means number of pointers is n, we have the size of each pointer, plus n minus 1, that means the number of keys we have in that node or in the memory block, multiply by the number by the size of the key, that is also 4 bytes. Key size is going to be equal to what? It is going to be equal to the memory block size, which is 2k bytes, or we can say 2048 bytes. Yes or no? So can we solve this? We can have n into pointer size is also given to us, that is 4 bytes. So n into 4 plus n minus 1 into key size, which is also 4, is equal to 2048, or we can say basically it is less than equal to that. So we can have 4n plus 4n minus 4 is equal to 2048 bytes. So we can also write it like this. It is going to be 2052 if you just rearrange it, and you will be getting what? So you have to take the floor of it. So you will be getting 256 as the order of this tree. So you will be getting this 256 as the order of the tree, or basically this particular block, right? Now, so we have found the order. Now we have to find the minimum possible height. So let's do it here. So we have the height here. We have the number of nodes. We are going to write the number of children we have. And here we are going to write the number of keys. So at height 1, that means at the root node, how many nodes are there? Only one node is there, like this, something like this. So I'm just showing you the structure, okay? It is going to be like this. So at height 1, only one node is there, right? What about the children? How many children are there? That is going to be equal to what? The order of the tree. Basically, if you see here, we have found that this block pointer, the number of block pointer is nothing but the number of children you have, right? So number of block pointer is what? The value of n, which is 256. So here we can write 256 here. And what about the number of keys? Number of keys will always be 1 less than the number of children that I have shown you in the structure. So if you have n pointers, so n minus 1 keys will be there. So can I write 255 keys will be there? Right, 255 keys will be there, or we can say those many records will be there, at the leaf node. So at height 2, how many nodes will be there? That is going to be the number of children, because those many nodes will be there at the second level. So it is going to be 256. And what about the children? It is going to be 256 square, 256 into 256, right? And the number of keys will be what? You can calculate this. So it is going to be 256 into 255. 256 into 255. And this will come around as 65280. But we have 1 lakh. We have how many records? We have 1 lakh records. So still we need one more level at least. So at height 3, how many nodes will be there now? That is going to be equal to the number of children we have at the upper level. So 256 square. And what about the children's? It is going to be 256 cube, right? It is going to be 256 cube. And the number of keys will be number of nodes. That means 256 square multiply the number of keys in each node, that is 255. And that will come around as something like this, which is a huge number, which is obviously it is greater than 1 lakh. So that means we need a height of B plus tree, height of 3 for this B plus tree, right? So that we can store this 1 lakh records. So minimum height required is 3 here. So 3 is the correct answer for this question. Clear? Let's solve this next question here. Consider a schema relation R having these 6 attributes A, B, C, D, E, F, and functional dependencies are given. The number of super keys for this schema we need to find out. Okay, so we have this relation having these attributes and these are the functional dependencies given. So in order to find number of super keys, first we need to find what? The candidate keys. Okay, then only we can talk about super keys. So let's find out candidate keys first. So here, in order to find candidate keys, you can see B is determining by A, D can be determined by C, F can be determined by E. That means B, D and F will always be there. What do we need? We need A, C and E. This is a way to find candidate keys. Okay, so this is a way to find candidate keys. So what you can say is ACE has to be there definitely in the candidate key, because there is no way by which you can determine A, C and E. You can determine B, you can determine D, you can determine F using ACE, but there is no way to determine ACE. That means in the candidate key you have to have ACE. Now let's find out the closure of ACE. So AC itself is already there. A determines B, so B is also there. C determines D, so D is also there. And E determines F, F is also there. All the attributes we are getting for this relation. So that means ACE is the only candidate key possible here. Okay, now let's talk about super keys. Super key is what? The superset of candidate key. That means if you have ACE, if you add any attribute out of this BDF, that is also going to be your super key. So any superset, ACE itself is a super key. If you add B, that is also going to be a super key. Let's say if you add D, that is also going to be a super key, because ACE itself can determine all the attributes. You can have ACEF also, that is also super key. You can have BD also, right? Similarly, you can have BF also, you can have DF also, right? So what else? You can have all the attributes also, because superset will contain everything. So BDF also. So all these are your super keys. The other way to find out here is the number of super keys will be 2 raised to the power n. That means where n is your all the attributes that you have in the relation minus the number of attributes that you have in the candidate key, which is 3 in this case, okay. If you let's say for other question, if you have 2 only, so it is going to be n minus 2. So it is going to be 2, n is 6 attributes you have, 6 minus 3, that is going to be 2 raised to the power 3. So 8 super keys are possible. 8 super keys are possible, and these are those super keys. So you can use any way, but this is much better because that takes less time. Okay, so 8 is the correct answer for this question. Let's see this question now. Question number 7. Consider the following relational schema. Employee relation is given to us, customer is given to us, sales represent ID is a foreign key referring to a employee ID of the employee relation. Okay, so this is your foreign key, and this is referring to this employee ID, which is your primary key for employee table. Fine. Now assume that each employee makes a sale to at least one customer. Okay, what does the following query return? So this is the query given to us. Select employee name from employee E where not exists, and then you have a subquery. Select customer ID from customer C where C.sales represent ID is equal to E.emp ID and C.rating is not equal to good. This symbol represents not equal, okay, to good. And we have to find out what does this query return. Okay, now carefully see here. First you have to see the inner query, the subquery. So if you see here, this query is a correlated query. Why I'm saying so? Because for each employee you are referring to this. For each employee you are running this inner query. As you can see, employee is there, and internally also you are checking E.emp ID. That means for every employee you are running this in the inner query. So for every employee you have to find what? Customer ID. That means those customers where sales, you have to find for every employee where the rating provided by the customers is not good. Okay, the rating you have to find for each employee you have to find where all their customers, because it's talking about all the customer IDs. So all their customers who have not give the rating good to that employee. Clear? You have to, for every employee, you have to find all the customers, those who have not given a rating good to that employee. Okay, so you can find out easily. Then if you see here, there is exist. What does that mean, exist? That means at least, if it returns at least one record. So if at least one customer is present, or at least one employee is present in that way. So exist means basically it is finding out at least one record. So do we have at least one employee, right? Do we have at least one employee for whom all his customers have not give good rating? That means they have given, all the customers have given bad rating. So do we have at least one employee like that? So that is the meaning. And then we have not. So here not means not exist. Now that is going to negate it. So do we have any employee, do we have at least one employee who have not received good rating from all his customers, right? Who have not received good, and this not is also present, so it is going to negate it. So basically we need to find what? Do we have any employee whose all customers have given good rating? Okay, so this not is going to negate by this one. This not is going to be negated by this one. So basically we need to find the employee, the name of all the employees from employee table E with all their customers having a good rating. Okay, so here if you see option A, name of all the employees with at least one of their customers having a good rating, no. Name of all the customers with at most one of theirs, no, that is also not the case here. Name of all the employees with none of their customers, no, none is not possible. Name of all the employees with all their customers having a good rating, yes, option D is the correct answer. So like this you have to solve it. Okay, you have to answer this. So that's it from this part of the video for GATE DA sample paper. We will be coming up with more videos on solving the questions for GATE DA from the sample paper that is provided by IISc. You can join our group. You can scan this QR code and you will be able to join, and you can connect with us and you can ask your doubts also. Fine. So like this session, share with your friends and subscribe to MindMatrix. And you can also visit our website www.mindmatrix.net.in for enrolling in our premium courses. I will see you in the next lecture. Till then, take care and bye-bye. Thank you.